Good afternoon, Evan Snowman here for Local, Making a Difference. Today we're doing our first video on the topic of sequences and series, and I'd like to make the point that initially a large amount of what we're going to look at is some revision of grade 11 topics, but leading to maybe looking at them in a slightly different way for the trick. So initially we would look at a linear pattern, okay, and we just need to remember that the simple word for a pattern is a sequence. And so we could look at something like 2, 5, 8, 11, etc. And we could say, using one of the methods from grade 11, that therefore, this thing being linear, we could see that therefore it would be Tn equals 3n minus 1. Okay. Now, there are a variety of techniques for that. One of them is by looking at the common difference and seeing that the common difference was adding 3 every time. And so because we're adding a common difference, it was linear. So when the first order difference is a constant, okay, it is constant, we would call it linear. We then looked at things like a quadratic pattern. Okay. So we could look at, for example, I don't know, let's try 3, 7, 13, I think works, 21 works, 31, I think works. Okay. And what we'd look at is say, well, hold on. The first difference, okay, is 4, 6, 8, 10. So it is not linear, and that's important to realize. Okay. But the second difference was a constant of 2. So it was a second order difference. And therefore it was quadratic. Okay. So we would know that therefore Tn equals an squared plus bn plus c. And while I know there are various methods, I favor the method that uses this diagonal, okay? And it would say to me that because I'm looking at that diagonal, okay, I would know that wrong color, I would know that 2a equals 1, sorry, 2a equals 2, which leads to a equaling 1. I would know that 3a plus b equaled 4. And this 2a and this 3a plus b are things that you learn, okay, which would lead to b equaling 1. And I would know from the blue line that a plus b plus c equals 3, which leads to c equaling 1. So as a result, I would know that my formula is Tn equals 1n squared plus 1n plus 1. Okay, there was also some work done in grade 11 regarding exponential, but not a heck of a lot went into it. Okay, and we will look at that in more detail now. Okay, so there was some look at exponential such as 2, 6, 18, 54. Okay, but not a heck of not all that much information went into it. Okay, we would simply recognize that because this thing was going up by, since it was multiplying by 3s, okay, multiplying by 3s, that therefore this thing was exponential. And your teacher may have pointed out to you that there must have been some tie-in to 3 to the power of n or something like that. Okay. Now, what happens in matric is we take a whole new view of this. Okay. And while you need to know all this information from grade 11, and we'll quickly look at 1 or 2 sums to revise that, we take a whole new look at this. Okay, so let's take a quick look at a pattern. Here are first 4 terms of a quadratic number pattern. Okay, write down the first values of write down the first term of the pattern. Well, we can see that this pattern is going up 15. We can see this pattern goes up by 0, goes up by 3, then it goes up by 6. So we can assume it's going to go up by 9, which means that the fifth term of the pattern, T5, will be 24. Okay, 3.1.2, find formula. Well, again, if it's going up by 0.36, then we can see that the second distance will be going up in threes. So therefore, 2a equals 3, a equals 3 over 2. We can see that 3a plus b equals 0. Therefore, 9 over 2 plus b equals 0. So therefore, minus 9 over 2 equals b. And we can see, hopefully, that a plus b plus c equals 6. And since we've got 3 over 2 minus 9 over 2 plus b equals 6, well, 3 over 2 minus 9 over 2 is minus 6 over 2, which is minus 3. So that's minus 3, and it goes across. B will equal 9. So therefore, we know that our formula, we put this all together, we know that our formula will be Tn equals 3 over 2 n squared minus 9 over 2n plus 9. And we're going to test that quickly by putting in, for example, the number 1. Put in the number 1, we're going to get 3 over 2 minus 9 over 2 plus 9, which does in fact equal 6. And that makes me feel slightly happy that we have got the correct value. So which term of the pattern has a value of 3,249? That's a typical London, New York sort of sum. Okay, where we're doing the reverse now. Okay, so we are now given a value and being asked to work with it. So we know that 3,249 equals 3 over 2n squared minus 9 over 2n plus 9. Therefore, 0 equals 3 over 2n squared minus 9 over 2n minus 3,240. So therefore, 0 equals 3n squared minus 9n minus 6,480 times through by 2. I can divide also by 3. So 0 equals n squared minus 3n minus 2,160. And I'm now looking, and I can now either use a quadratic formula or factorize it. Because of this n at the back end here, we know that the one n value, the one result will be positive and one result will be negative. And again, we know that n has to be a positive whole number. So when we plug it in, we get answers of, again, quickly just grabbing my calculator here. Cool. We get answers of and it was 48 and minus 45. Okay, so we're getting an answer of, therefore, get answers of n equals 48 or n equals minus 45. We can realize that this one here is not valid. So we know that T48 has a value of 3249. Okay, so 3.1 is a nice revision of a quadratic formula. What I liked here with 3.2 was it, and I've seen it now in two of the exam papers, was they give us a sum which involves a something unusual with a trig equation here, and they ask us to find out, but they tell us that this thing is arithmetic. Now, this is the first time we're meeting this new word, okay? And this is probably one of the key differences between this and the grade 11 syllabus, is that they use a new language. And it sounds quite kind of silly, but all arithmetic means is linear, okay? So an arithmetic sequence is a linear sequence. It is one which would have an equation that looks something like Tn equals Tn equals Mn plus C. Okay? But what we do know about linear patterns is that the difference between the terms is the same. So we would know that therefore 2 times sine of 3x minus 1 would be the same as 5 minus 2 times sine of 3x. Okay? Because we're saying here that t2 minus t1 equals the same as t3 minus t2. Okay? Now, we build on that a little bit more with arithmetic sequences, but what we're saying here is that the difference between the two terms is a constant, and we're building on that more strictly. So when I bring that over, I'm going to get 4 sine of 3x. That minus 1 becomes minus 1 becomes plus 1, goes across, equals 4. So sine of 3x equals 1. We know from a sine function doing that therefore 3x equals 90. Why don't we need to worry about the period descriptor, etc.? Because they say to us only in that interval. So we don't need to put in that period descriptor. Okay, the repetitions. So we know it is only equal to 90. We divide by the 3, and x equals 30. So all we needed there was the courage to work with a trig value. It actually fell away quite quickly, but also we needed to know this new language that we were talking about, linear. And so the difference here is that we now, of those things which we had previously, which was linear, quadratic, and exponential, okay? Well, from a trig, the good news is that we do not take the quadratic any further. You still need to know it from grade 11, but we're not going to deal with it any further in the trig. Okay, for linear, we are saying that this is now called arithmetic. Okay, and for exponential, we're saying this is now called geometric. So any formula, any sequence or pattern that they now tell you is geometric, you know is actually linked to a exponential pattern, and any pattern that they label as arithmetic, you now know is a linear pattern. Now the key thing is to know the formulae. And the formula for an arithmetic pattern is that Tn equals A plus n minus 1 d. And the pattern for geometric is Tn equals A r to the n minus 1. Okay, a couple of things that we need to discuss. Firstly, okay, please notice that both of them have an n minus 1. Okay, and that is important to recognize. That is, okay, and secondly, both of them have an a value. Okay, now what is always true, okay, what is always true for all functions, for all patterns, is that T1 will equal A. Okay, so the first term is always equal to A. Okay, that's the reason for the choice of A. Okay, in the case of a arithmetic, we've seen already that D equals T2 minus T1 is the same as T3 minus T2, etc. Okay, it is the difference between any terms, so D for difference. Okay, since we are often talking about adding or subtracting a constant, but therefore talking about D for difference. Okay, we've added to get the next term, then we would subtract the one term from the other term to find the D value. Okay, in the same way, R would be the common ratio. So R would be T2 divided by T1, which is the same as T3 divided by T2, etc. Okay, now what this does lead to is a useful little sub-formula, which isn't really all that common, but can sometimes be useful, which is that if I was to rearrange the terms on this side, 2T2 equals T1 plus T3, and alternatively here, R2 squared equals R1 times R3. That can be useful, okay? But the key ones to know are the two that I'm highlighting here in the blue, or underlining here in the blue, which is this one here and this one here. Okay, that is key to know. So we're taking a slightly different approach now to it, and you'll see that, as I said, they both have commonalities about them. They both use the letter A, okay, and they both use this n minus 1. This notation that changes for which we were using in grade 11. Okay, we're no longer dealing with arithmetic. We're not going to focus on the quadratic, and we are now describing the exponential as geometric. Okay, so again, a revision of grade 11 work. No major surprise here. So again, despite me telling you all about the new matric work, the reason I've included this at this point is to remind you, please don't forget that the grade 11 work is half of matric. Okay, so minus 2, 0, 3, 7. Again, we've seen so many of these, we should be getting quite quick at them. The first difference is 2, 3, 4. So we know it's not linear. Okay, or we could say it is not arithmetic. Okay, the second difference here is 1, 1, 1. So we know that 2a equals 1, a equals a half. We know that 3a plus b equals 2, but if a equals a half, therefore we know that b also equals a half. And finally, if a plus b plus c equals minus 2, okay, then again we know that a half plus a half, so therefore c equals 1, and we have our formula. Okay, now I have jumped the gun a little bit because I didn't actually go and read the instructions, but you know that at some stage they're going to ask you for the formula, and the formula is the key to doing these types of sums. So going back one, okay, what's the next value of the sequence? Well, we can see that we're adding 2, 3, then 4, so we're going to add 5 to the next one. So T5 will equal 12. 2.1.2, we've got the expression for the nth term, and same as previously, what's the next? Which term will have a value of 322? We can plug that in and do that. I'm not too interested in that. Okay. What I'm interested in now is looking at this. Okay. Here is a fairly straightforward sum using the new notation. Okay. By talking about R, okay, they mean that we must be dealing with a geometric. Okay, and we know from the formula sheet or from our own studies that Tn equals A times R to the n minus 1. So the first thing I'm going to do is to find the general term of the sequence of the series, I'm going to plug in these values. So 3.1.1 Tn equals 2000 times 1/5 to the power of n minus 1. Okay, no biggie. Now they talk about T of 7. So 3.1.2, again, if I was to just talk it through it in a slightly different voice, well, what's happened on the left? N has been replaced with 7. So what's going to happen on the right? I'm going to simply replace N with 7. So that's now going to be a 6. And I'm going to trust my calculator. So 2000 times to the power of 6. I get an answer of 16 over 125, 0.128. Okay. Which term will have a value of 16 over? That feels weird. Okay. Okay. So we now need to be able to, again, New York, London, they now give us a value and want us to find the n value. Okay, so 3.1.3 of the term. So Tn equals 2000 times 1/5 to the power of n minus 1 equals 16 over 15625. Okay, so we're going to take that 16 divided by 15625. I'm going to divide by 2000. I'm getting an answer that's massive. Okay, so 1/5 to the power of n minus 1 equals 1 over some massive number, 1,953,125. Okay, well, we know that this is going to be equal to 1/5 to the power of some value. Okay, we don't know what that value is yet, but we think we can think along those lines. But what we're going to do is we are going to therefore realize that because we're looking for a power, okay, I'm going to take a log. So what I've got here is, okay, therefore n minus 1 equals the log base 1/5 of this number. And I do that, and it's so cool. Let's have a look. Log, and it gives me an answer of 9. So n minus 1 equals 9. So therefore, the 10th term of the series will have that value of 16 over 15625. Please remember, I'm not looking for n minus 1, I'm looking for n. Okay, so the key point I'd like to make here is we're now able to talk in more advanced terms about a geometric sequence. Okay. However, what is important is because we are now working with this new notation. Okay. Because we're now working with this new notation. Okay. We were saying that therefore, for a sequence. Okay. We know that it's always true. Okay. That T1 equals A. Okay. We now are saying that if the thing is arithmetic, okay, if this thing is arithmetic, that Tn equals A plus n minus 1 d, where d equals T2 minus T1 equals T3 minus T2. If the thing is geometric, we know that Tn equals A times r to the n minus 1, where r equals T2 over T1, or alternatively T3 over T2. Okay, however, what is also the reason why we've changed this notation to arithmetic is it allows us to now talk about what is known as a series. Okay, and the key thing about a series is that if I had any sequence, and it makes no difference what we talk about with any sequence. So let's pretend we were shopping, and the things we bought cost 3 Rand, then they cost 10 Rand, then there was something which was 7 Rand, and then there was something which was 12 Rand, and then there was something which was 100 Rand. Okay, so here we have a sequence. Okay, ostensibly it looks fairly random. Okay, and we can see that T1 is 3, T2 is 7, T2 is 10, T3 is 7, T4 is 12, and T5 is 100. Well, imagine I was keeping track of my shopping trolley with a running total. Okay. Also, you might know this from statistics, that would be your cumulative frequency. So at this point in time, having put one item into my basket, I would have 3 Rand. Having put the second item into my basket, the total would be 13 Rand. Having put the next one in, it would be 20 Rand. Sorry. Okay, it would be 20 Rand. The fourth item goes into my basket, my running total is 32 Rand. The fifth item goes into my basket, it is 132 Rand. Okay, now this effectively is a series. Okay, and we're saying here that this value here in the fifth place is now going to be referred to as S5. And S5 is nothing more than T1 plus T2 plus T3 plus T4 plus T5. Okay, and probably one of the more tricky things here is keep track of what we mean by a sequence and what we mean by a series. So a series is the sum of all the terms up to that point. Okay, so a series is the sum of all the terms up to that point. Okay, what that does also mean is that since these four terms here would actually form S4, that we actually have a quite nice little formula which says that S5 is the same as T4, sorry, apologize, is the same as S4 plus T5. Okay. Now, effectively, what I'm saying is that if I've got a shopping trolley and I'm putting my fifth item in, I don't go recount all 5 items. I simply take the total from the first 4 items and add in the fifth item. Okay. Now, generalizing this formula comes out to the following. Okay. As a result, Sn equals T1 plus T2 plus T3 plus until we get to Tn, or alternatively, S of n equals S of n minus 1 plus Tn. Okay, the key to this is to remember that Tn refers to a sequence and S of n refers to a series. Okay, so let's go back to our previous slide. Now that we know what a series is, and let's go and look at the formulae. So what we have now is a formula that says that S of n equals n over 2 times a plus, times 2a plus n minus 1 d. And that the geometric series is going to be S of n equals a times r to the n minus 1 over r minus 1. Alternatively, some people refer it this way, 1 minus r to the n over 1 minus r. Now, again, what I'd like you to notice is this appearance of the n minus 1. It's not quite as obvious in the green example, but you can see you can see an n and a minus 1 if you look for it. Okay. But what I want to quickly comment on is that in all four of these major equations, there is t, a, n, and d. There are 4 variables. There is t, a, r, and n. There are 4 variables. There's s, the same n value, so I'm not going to count it twice, I'm going to count it only once. Okay, a and d, 4 variables, s, a, the same r value, and n, there are 4 variables. So again, all of these equations, all of these formulae have got 4 variables, so the technique here would be to identify 3 in the text and to plug and play into this formula. Sometimes you do get an advanced question where there are information where you only get 2 pieces of information and you would need to use simultaneous equations, but that is something we would look at in a later video. Okay, but in principle, because you've got 4 variables in your formula, you would therefore substitute in 3 variables to find the missing one. Okay, so having made that point, I'd like to quickly go and look at the fact that actually there is 2 extra things I need to point out to you. And one is that because of its use in some of the formulae, S of n equals n over 2 a plus L, where L is simply the last term. Okay, now that one does not have 4 variables. It does still have 4 variables, S, N, A, and L. Okay, but it's a very specific one which uses L as the last term. Okay, finally, there is one extra piece of information. Okay, if this is arithmetic and this thing is getting bigger, then we can really understand that as n gets bigger and bigger and bigger, S, the sum to infinity, will always equal infinity, or negative infinity. I'm going to hedge my bets here by saying positive or negative infinity. However, geometric pattern is very interesting because if r was bigger than 1, okay, or r was less than -1, okay, then the sum to infinity would equal positive or negative infinity. Okay, I know I'm not writing the positive plus or the minus sign there. I'm aware of that. Okay, so there's a plus minus sign where this yellow dot is, and I know I'm leaving it out on purpose. Okay, because what I want to make is the point that, and however, if r was trapped between 1 and -1, okay, so if r was a true fraction, if r was a value that was between 1 and -1, okay, r to the n, well, let's think about it. Any power, okay, if you have a fraction like a half and you square it, it becomes a quarter. It actually becomes smaller. Times by half, so a half cubed is an eighth. It becomes even smaller. So what's going to happen is this value here is going to head off to become 0. Okay? And if it heads off to become 0, what we now have is a useful little extra formula that is only available for geometric series, and that is that the sum to infinity would be equal to a over 1 minus r. Okay? And that formula is something which is useful and important to know. So what we have here now is a formula that under specific conditions, we can work out the sum to infinity. Now, again, because we're involved in a chapter where they've changed the language, they talk about this formula as a converging sequence. And if that is converging, then this upper one would be what we call diverging. Okay? So in this chapter, the key thing is to understand that it's actually not all that difficult theoretically in terms of its, in terms of its complexity, because we're given the formulae on the formula sheet. All we really need to do is to decide, are we dealing with a sequence or a series? Is it arithmetic or is it geometric? Apply the correct formula, find 3 values in the text, plug and play. Okay. However, okay, we will look at 1 or 2 extra things just to make it a little bit more fun in the next topic, and I hope you will join me for that. Thank you so much.